I'm going to start writing code, and I will show you the excellent pseudocode language that we will use. It is the best way to write large systems that have failures, that have concurrency, and that are distributed, and that you want to prove correctness. It's a layered event-based component model. It's better than any programming language that exists. It's even better than Oz. It's better than Erlang. So why is it not a language? Well, because people are connected to history using stupid legacy stuff. That's the only reason I can imagine. So this is really the pseudocode we're going to use. I'm going to explain it. But that's only part of making the system. The other part is the specification, because you want to know what you are implementing. And that's two parts. One is what the programmer defines, which is the interface and the properties, the correctness properties. So this is the programmer who defines it. But on top of that, you have the environment, what you're forced to use. Maybe you are forced to run it on the internet or on a cluster or on something. And that's the system model. And if the system model is kind of bad, then you'll have a hard time writing algorithms. But if the system model is easy or good, it will be easier. Remember we talked about asynchronous, synchronous, partially synchronous. That's the system model. And if you change that a little bit, you can go from an easy algorithm to an impossible algorithm. Okay. Also the kinds of failures you have. That's imposed on you. Node or channel failures. So here we're going to start writing some code today. But we won't really get into the hard algorithms until later. But I will already start writing some code here. Okay. This is kind of the overview we're going to talk about today. And we're also going to talk about safety and liveness, which if you have not heard of them, it's very good that I talk about it because you have to know what these two are. It's fundamental. Okay. So all of that is fundamental. But before I get into all that, I have a small thing to finish from last week, which I will do now. Okay. And as is my tradition, it seems to be a tradition, I will first ask for a few minutes of silence, a few seconds, for the people in Ukraine fighting for their freedom and ours. Okay, which is still going on, unfortunately. Okay, so last week we gave the formal model, but I won't talk about the formal model anymore, except to you kind of use it. What I will talk about is the execution complexity, how long things take, and how many messages. And the neat thing here is I will present to you something I call the paradox of time complexity. And I will see whether you guys can figure it out. Okay? Okay, so complexity, it's important, of course. It's efficiency, basically, yeah? Efficiency is a real basic thing. If we didn't care about efficiency, if all computers were infinitely fast, then everything would be easy. But that would make life much too boring, okay? So the universe is not like that. The universe is designed to make life interesting. After many years, I have figured it out. It's designed to make life interesting. And one of the ways it does that is that things take time. And so let me talk about the number of messages and the time it takes for an algorithm. Okay? And when an algorithm goes into a terminated state, of course, is when it terminates. And an algorithm terminates when all states in a configuration are terminated And there's no more messages in the in-out buffs. So you understand what that means, huh? The configuration is the state of the whole distributed system. A state is a state of one node, huh? Remember that. Remember what we said, huh? That's the whole system. And the network is empty. There's no messages hanging around in the network, so the in and out buffs are empty, okay? If we have that, then it's terminated. Okay, that's clear, huh? So network and all the nodes, configuration. Okay, very good. Okay, the message complexity, how many messages it takes. But in fact, we're running algorithms. So depending on how we execute, depending on what we do, the number of messages might be different. Okay, so the message complexity is the maximum number of messages for all admissible executions. So it's a worst case complexity. That's the normal way we define complexity. Yeah? It's the worst case. You can also do best case, but if you really want to make sure that you design your system well, you have to worry about this. Okay? So remember what admissible means. It means it's like fairness. It's exactly fairness for the processes, which are like threads, plus the messages are delivered. Okay? And because we're in an asynchronous model, all the executions are infinitely long, but it stops some finite time there. But infinite because we don't know how long it takes. Okay, so that's the message complexity. The time complexity is a little bit more subtle. We're not going to actually measure the millisecond time. We want to have some kind of more abstract notion of time. We want to abstract away from the actual speed of the network. So we're going to talk about message delays as taking a certain time, as units. So a message delay will be at most 1 time unit. So a message travels, that's 1 unit, okay? And we will assume computations are 0. That is the normal, reasonable approximation. You can always do differently if you have big computations. But in many cases, this is good. Okay? And we're going to measure our algorithm by piggybacking times. And that's called a timed execution. Each comp event, so each computation in a process, there will be timed. And it's always increasing. Okay? The first one is time 0. And each time you do a comp, it will increase. Okay, and when you send and receive a message, the maximum time is 1, because the message takes maximum 1. Okay, so a message in this model will either take 0 or 1 time unit. Okay, it's abstract time, but it's actually very good for analyzing algorithms. And of course, we're looking at all the admissible executions. Yes?
But in this model, how do we model the fact that if a message is received before another, it changes the computation? If all messages take 1 time unit, how do we tell?
Well, because we have chains of causality. So if I have a message received, and this causes another message to be sent, then we will have 2, of course. I'm not sure I really understand.
No, if there are 2 messages sent simultaneously, but you receive this one first, and because you receive this one first, and this one, that changes what you compute. Okay, so this is abstract. If I send 2 messages from one process to another, they can actually arrive at the same time in this model, the abstract time. If they both start at time 3, they both arrive at time 4, for example. They're in parallel, okay? It depends on when you send a message, there's already a time when you send it, and when it's delivered, it's 0 or 1 more. That's it. So it could be the same, because it's actually an interesting point. Why do messages take 0 or 1? It's actually very interesting. In fact, it's very important that messages are 0 or 1 in this model, and not exactly 1. Because exactly 1
actually that's wrong. That means the system behaves wrongly. We have to allow the 0, because messages are not, otherwise it's much too synchronous in a sense, okay? So this abstract model, the messages will take 0 or 1, okay? You see? I'm not sure if anything I'm saying is not clear, ask. I'm not sure if I answered really your question.
Kind of keep down the problem of the order of the messages.
I mean, with this model, you can compute the times, and you can calculate a number, which is the time. If I send 2 messages at time 3, they will both be delivered at time 3 or 4. And if one of them is delivered before the other, that they would be either both at 3, the first one at 3, the second one at 4, or both at 4. That's the only possibilities. Because time is always increasing, never decreasing, and messages take 0 or 1. It's the only constraint. So it's very simple. You don't have to look more. It has nothing really to do with causality, yeah? It's basically just counting the number of message delays, in fact. Each time a message comes, that's 0 or 1. It's not actually just 1. It could be 0 for a message. Okay? That's the model. It's important that it's 0, and I will explain why, and that's part of the paradox that I want to explain. Okay? So in this model, when we calculate the time, messages are taking at most 1 time unit. That means they take either 0 or 1. Now another model would say messages always take exactly 1 time unit and never 0. So let's compare those 2 models. First, let's try to compare them semantically, okay? If I look at a bunch of executions, okay, the at most model is actually subsuming the exactly 1 model. You can have other executions in the at most model that don't exist, because at most it could be 1, so it's the same as exactly 1, but you can have also 0, so you can have more executions. So the at most 1 model actually has a bigger set of possible executions, okay? So here's an example algorithm. This is a simple algorithm that I want to present to you. This is a broadcast algorithm, okay? The code here, these 2 pieces of code will execute on all nodes. Each node has 2 local variables, a parent, and there's also n, which is a constant, which is the number of nodes. And the way you do it is you have 1 node, which is the source, and it's going to broadcast to all the other nodes. And the way it works is it sends a message, let me call it A, to all its neighbors. Remember, each node has some neighbors. And then it waits until it receives replies, which are the B messages, okay? Until it receives n-1 Bs. And all the other nodes, they execute this code. And there's 2 possibilities. Either they receive an A message from a node P. If they don't have a parent yet, if the parent variable is null, then P is set to be the parent. So basically, the first node they receive A from is the parent, okay? And they forward the A message to all neighbors except the parent. So if you have a node, let me show an example. So here's a simple network. Here's a source. You have some nodes here. Let's say this one is the source. If it sends an A message here, if this node, which is, let's say, node X, receives the A message, then it will forward the A to these 2 other nodes, okay? And it sends a B to the parent. So this is an acknowledgement that it got the A. And so the source will wait until it gets n-1 acknowledgements, and that means that all n-1 nodes have received A. So when this node receives A, it sends B to the parent. And when a node receives B, it just forwards it up. The parents are basically the way back to the source. So the A node here goes down. Notice that this one will then be the parent. This is node X. The A nodes go here to the end. So they keep going down. Okay? If there's no neighbors, then this one does nothing. But then the B nodes, the B messages come back. So the B message will come back here, and it will go back up to S. Here also, the B messages will go back. So every single node will originate a B message, and when a node is in the middle, it just forwards the Bs. Okay? So you see that eventually what's going to happen, so there's assuming no failures here, is that the source node is going to receive n-1 Bs. And then when it does that, it knows that all the nodes have received A. So that is the termination of the broadcast. You see how the broadcast is working? You clear on how it's working, everybody? If you're not clear, you ask. Because I'm going to ask you a question about this algorithm. I want to talk about the time complexity of this algorithm. What is the time complexity if every message takes at most 1 unit? And what is the time complexity if the message takes exactly 1 time unit? It depends on the topology, It depends on the shape of the graph. So there's 2 questions here. And the point, the paradox, is that the at most time complexity in fact is higher than the exactly 1 time complexity. You see what I'm saying? If we allow messages to go faster, the algorithm runs slower. You see that? That's what I'm claiming here. I'm saying the at most time complexity, when we analyze this algorithm, is in fact strictly greater, depending on the topology. For particular graphs, it will be strictly greater than the exactly 1 time complexity. That seems a bit strange, no? Doesn't it? If we allow messages to take 0 time, the algorithm actually slows down according to time complexity. So that is that is correct property. That is what I call the paradox of time complexity. So you have to understand why it's like that. So that's kind of the exercise for you, is to understand why it's like that. If you go from exactly 1 to at most 1, it can only increase the time complexity. Because every timed execution with exactly 1 is possible in the at most model. So if here we have a set of executions in the exactly 1 model, it's a subset of the at most 1, because all of these are also correct at most executions. But the at most model has additional executions where messages take 0. And the time complexity considers the maximum over all this. Okay, it's the maximum of the time over all the executions. And so because with that most model we have more executions, strictly more, the time complexity of the at most model can only increase. You see that? So formally, because of these definitions, it's clear, I've just shown you rigorously, that the at most model, it can never have lower complexity. It will either have equal or more than the exactly 1 model. See that? Okay? And in fact, you might say, well, maybe it's equal. But no, in fact, for this algorithm I showed you, I can show you graphs where the at most complexity is strictly greater than the exactly 1 complexity. Okay? And so the exercise for you that I will not answer today is to understand that, is to show me an example where the at most time complexity is greater, strictly greater, than the exactly one. And I will give you a hint. Okay, assume now in our algorithm, the A messages, the ones going down, they will take 0 or 1. The B messages take 1. Now I'm going to give you a strong hint. Because A is 0 or 1, a long path of A's could be fast, because they may be zeros, but a long B path will always be slow. Okay, that's just a hint. I'm not going to give you the answer. Okay? So this is an exercise for you to do by yourself. You can discuss, but try to figure it out by yourself. Or maybe you already know now. Okay? Do you understand what I'm asking you? Is the question understandable? The question is, for this algorithm, show me a graph and show me why that the at most complexity is strictly greater than the exactly one complexity. That's the question, and I will kind of ask you to do it as an exercise. Okay? It's clear? The question is clear? Yeah?
So do we have to compute the time the source has to wait to receive the last B message?
You have to, until termination. So you have to compute the complexity until the source completes and receives n-1 B's. Absolutely, yes. So this algorithm terminates when the source receives n-1 B's.
So if we take the exactly one time unit and there are two processes, it sends one, that's one, and then B.
But
yeah.
But be careful. There are many possible executions. If two nodes send messages to the same third node, the order of arrival could be different, and that would give you two different executions. Okay, and the time complexity is the maximum over all possible executions. The only condition on the executions is fairness. That means that nobody is starving, everyone goes forward. But there's no assumption on the order of message arrival. Okay? You see that? So there can be many possible orders of A's and B's going through this system. And you have to, the complexity is the maximum complexity over all possible executions.
If we're just summing integers, why would the order matter?
Yeah, good question. You tell me. Yeah, exactly. Why would it matter? Yeah, that's a very good question. Please, I want you to answer it. Interesting, no? It's not obvious, maybe. It should become obvious at some point. Okay, I'm not expecting everybody to immediately get the answer to this, but this kind of reasoning is important because behavior of distributed systems is sometimes non-intuitive, okay? Okay, you see that? Okay, let me go on now. This was the finish of last week. So this is an exercise for you. So I will come back to this next week, and we will discuss it. I hope some of you have answers to give me, okay? Okay, so let me now talk about today's course, which is writing the code, specifying and implementing distributed systems. Okay, so we're looking at large distributed systems. Here's an example. So we have, each of these is a node, we have communications, we have a whole bunch of middleware. So middleware is like the libraries that you use, and you have applications on top of this. And this can be a very big application, okay? And we're interested in the core algorithms, very important algorithms that are like services, okay? And you need something like this. These services are stronger than network protocols. Broadcast is stronger, or consensus, it gives you an additional service over TCP, which is just a reliable byte stream. Okay, So in this course, we're going to build on top of network protocols, okay? For example, TCP is only one-to-one communication, one process to another, reliable byte stream, but maybe we're interested in groups of communication. Maybe we're interested in reliable broadcast, where all nodes are informed. Maybe we want the broadcast to respect causality, like we saw last week. That gives another element called causal order broadcast, or total order. Remember the very first lecture, I mentioned total order broadcast. And then a very interesting one called terminating reliable broadcast. Because when you do a broadcast, normally the single node will not know when the whole system has finished the broadcast. The single node only knows when it receives. But to know when the whole system has terminated, that's another algorithm. Because the nodes have only a partial view. Remember the views? The nodes can only see what they send and receive. They don't see the whole system. They don't have the God's eye view. Nobody has that, okay? So terminating reliable broadcast tells the node when the whole system is done. And maybe you want even more, shared memory, like a database. Maybe we want a distributed database with the memories replicated for reliability, shared memory, consensus, so that there's agreement, atomic commit, which is a form of consensus, or group membership, where you have a group of nodes that are kind of working together, and you send messages to the group, but the group can change in size. All of these are services on top of network protocols, okay? They're called high-level services, and that's kind of the focus of this course. So this course is complementary to network protocols. So my colleague Olivier Bonaventure gives you a course on networking. I'm not going to talk about that. We're going to assume the networking is working, and we're going to build services on top of that, okay? Okay. And we saw already some examples. Reliable broadcast. This is a broadcast algorithm that works even when you can have failures. And when you broadcast a message, there's two possibilities. Either all nodes get it, or none get it. There's nothing in between. Even if you have nodes failing, you're sure that all the nodes that don't fail will get the message. Even if some nodes in the middle are failing, somehow all the nodes will get it, or none, and there's nothing in the middle. This is called reliable broadcast. So this happens despite failures. This is a very nice service, huh? It's not like when you just send messages to nodes, if you have nodes failing, the message will be received by some of the nodes and not by the others. That's not very nice, huh? What you really want is everybody, even if you have failures. So reliable broadcast is stronger than the naive broadcast where you're just sending. But this takes an algorithm. This is not so simple. This takes an algorithm that works in a concurrent setting with failures. So we're going to write the code for this. Another one is atomic commit. I mentioned this one already. It's a kind of consensus. The nodes are deciding now. All the nodes are deciding. But they have to reach the same decision, despite failures, despite delays, despite concurrency, they have to reach the same decision. And here it's whether to commit or abort a transaction. Super important, because if you didn't have this, then you would not have banks. Then the banks would be run like Gringotts, where the goblins are writing on little pieces of paper. But if you want to computerize this, you need reliable, distributed, replicated system. So the nodes have to reach the same decision. So that's a very important service. Okay? So this is the kind of stuff we're going to write. And the code we're going to write will be for doing that. Okay? So let me explain to you now the pseudocode. So this is not really a programming language. It's a pseudocode. It's kind of a language, huh? But it's a pseudocode because there's no really a system doing it. Erlang comes a little bit close, but it's doing things that no language is doing, but it's very nice. But it's still a pseudocode. So you have to translate it into whatever language you implement it on, okay? Okay? So the way it works, you have, each node is a single program. You have a global clock, and each node does a step each time. Okay? Each node will either do a local computation or deliver a message. So it's interleaved, okay? The nodes are doing interleaving. This is semantically, yeah? Even if you have multi-core, it's doing like this. Okay? And what did we see last week? Well, here's 3 models of distributed systems. The model we saw last week has in buffs and out buffs. And the way it works is that when you do a computation, you will empty all the in buffs and send one message. So it's this one, it's the third one. Receive K messages and send at most one message to each neighbor. This is the model we saw last week called Etienne-Welch model, because in the book of Etienne-Welch is the model they define. But there are other models where you can at most receive one message and send at most one message, or you receive one and send one. So the model by Rashid Garawi or by Nancy Lynch, okay? So it doesn't really matter, okay? We saw this one, which is a reasonable one, but others are also reasonable and might have different ones. So it doesn't really matter as long as they're interleaved, okay? That's one thing. Okay, each node, so which is like a hardware processor, consists of what's called components. A component is a running piece of code which is forming kind of a software stack. Okay, and I will be using these yellow boxes, and I'll explain because there's a specific concurrency model here. This is the basic piece of code I'm running. This is sequential, okay? This is sequential, and you have 2 funny things, one called upon event and the other one called trigger. Okay, now I have to say something. The book by Garawi and Rodriguez, which is traveling around somewhere, I'm not sure who has it now, just show it, huh? All the code in this book is written in this model. And so the code I show you in this course will be coming from that book, most of it, except the stuff that we write extra. And so I'm using the notation and the terminology from that book. So if you don't like my terminology, don't shoot me, shoot Garawi and Rodriguez, okay? Because they're the ones who came up with it. So upon event is like receiving a message. Why isn't it just called receive? I don't know, because it's event. Okay. This is receiving a message, and this is the message, which is like a record. And trigger is a send. Why isn't it just called send? Well, because it's called trigger. Okay. But it's sending a message. So basically, you have a sequential piece of code. You wait for a message. When that message arrives, then this becomes executable. But then it depends on the scheduler. If the scheduler picks this guy, it runs it, and this is single-threaded, this yellow box. And when it does a trigger, it will do another send. So the sends are asynchronous. Basically, it just puts the message in the out buff, and the network, then the model takes care of the rest. So the trigger will not wait until the message has arrived. Okay, so that's the basic piece of this pseudocode. It's a sequential piece of code that waits for a particular message. When that message is there, it executes sequentially, and it's able to send messages, but without waiting for the result. So send that are asynchronous. Okay? So that's how it works. The reason why the upon event is not called receive is because it's not just messages, actually. They call it events. It could be messages, messages coming. A message comes and you execute, but it could also be timers. A timeout of a timer. You set a timer, and when the timer times out, it's an event. Or it could even be a Boolean condition. If there's a local variable which has a certain value, then when that value becomes true, then that piece of code can be executed. Okay? So these are events. Okay? And now, the interesting thing is that we have a layered architecture. We have layers of these yellow boxes, and messages can go down the layers and up. Okay? And messages that go down are called requests. Messages that go up, which are like responses, are called indications, which is very strange. Don't shoot me. Shoot Rashid Garoui and Luis Rodriguez. I know both of those guys. They're very nice. They're very friendly. They would love to have a beer with you. So please don't shoot them. But you are allowed to criticize them. Okay. So this is a weird name for a response. You also have confirmations, which is like an acknowledgement. So the code kind of looks like this. Okay, so on a single node, you have these yellow boxes. Each of these yellow boxes has these upon event pieces of code in there. And they're all kind of executed concurrently. So each of these is like a separate thread, okay? So for example, here on the bottom I have some piece of code doing network protocol. Let me call it perfect link component. On the top I have some database thingy. In the middle I have reliable broadcast here. I have consensus here. I have a commit here, which is using the reliable broadcast. And it's like layers. So when we write the code, we're going to write the code in these yellow boxes. Okay, and we're kind of going to build the system in layers, like Lego blocks. We're going to start from the bottom and we build up. Okay, and each of these boxes, the code will be kind of simple, I hope. But the whole thing will be doing very sophisticated, fault-tolerant concurrent computation. Okay? So the way it works is that, let's say the database needs to do something. It sends a request down. It wants to do transaction. Sends a request down, so the message goes down. This component runs some stuff. This component can send its own messages further down. This one, reliable broadcast, can send messages down. And each of these components might also send replies back, which are indications. Okay? So it's really layered abstractions, which is a very reasonable way of building things. So the commit component might be using reliable broadcast. Reliable broadcast is using perfect link. Okay? So the database doesn't know about all that. Database only talks to the commit here. Sends a request, gets indication back. But this commit component might be doing lots of stuff, and it sends its own messages down and gets its own results back. Okay? You see how that works? And so we're going to be writing the code in these yellow boxes. And today I will show you some examples. And the whole first half of the course, we'll be writing lots of code in this way. Okay? And we'll try to make the code inside the yellow boxes very simple, to make it layers so that the simple thing, the complicated things are done piece by piece. Okay? There's a few semantic things. If I send multiple requests down, they are sent in FIFO order. That means the order is maintained. If I send two messages, then they will arrive in the same order. So locally, inside a node, the FIFO order is maintained. They don't switch order. Okay? That's very reasonable because we're inside the same computer here, right? This is not a network. This is inside the same computing node. Okay? So that's how one node works. Okay? Now, like I said, a send instruction is called a trigger, and a receive instruction is called upon event. And what do I send? It's like a record here. It's like pseudocode, so I'm just going to put in whatever data I want here, and then there's kind of like a label telling me the type of the thing. Here, and for the received message too, there's going to be a bunch of things in there. So I'm not going to be worrying about the data structures. I'm going to assume any data structure I need is available. If I need a set, I have a set. If I need a list, I have a list. If I need a record, I have a record. Okay? So this, because it's pseudocode. Pseudocode is easy. So that's one thing. So let me now go just back here. Look at this request. It's going down. Here, the beginning of this arrow is a send. So it's a trigger. The end of the arrow is upon event. So a request is a send received that goes down. But look at this indication. The beginning of the arrow is also a trigger. It's also send. And the end of the arrow is upon event. That means the request is always going down, but a send could be either going down or up. The trigger can be a trigger implementing a request going down, or it could be a indication going up. Okay? So that's kind of the main difference in terminology between request and indication. The whole point is that you're going down in the abstractions, and the indication goes up. Whereas trigger and upon event does not assume the direction. Okay? Trigger is just a send. It could be going up or down, and upon event is just a receive. Maybe it receives from higher up, or it receives from below. Okay? Okay, then the whole system then looks like this. So each of these big boxes is a computing node, P1, P2, P3. And on each of these nodes we have this layered architecture. And the nodes communicate only through the bottom level. Okay? You have here these channel code here, which this is the networking layer, in fact, this part. And all the code we write is here in the middle. Okay? So we're going to be writing code here, for example, broadcast, and then applications on top will be using that code. So this is a very reasonable way of doing it, and using the pseudocode, we'll see it's actually quite easy to understand, I think, but I hope you will think the same. Okay? So that's the code. So I've just shown you this. I haven't shown you much code, but I will show you code in a few minutes. Okay? But now we're going to look at the specification. So basically, I'm going to go through this part now. I showed you this now. Now we'll go through this part. Actually, it takes more time to explain the specification than the implementation. Question?
So what's the name of the message that I send between two modules in the same layer of abstraction? Or is that not possible?
It's a message.
Not a request or indication?
No, it doesn't have a particular name. It's just a trigger. And no, request is going down on one node. The request and indication are changing level of abstraction. It's going down in the layers. But you can also have messages that are horizontal, so they will not be doing that. They're just triggered. They don't call request or indication. That's part of the messages inside one layer. But we'll see it. They're not in the code. Request and response, an indication. You see it in the interface, but in the actual code, you'll only see triggers and upon event. The word request will not appear here. It's something that you know when you build the system. But the code will just be upon event and trigger. Whether the upon event is from higher or from below, that's part of the specification. You won't see it in the actual code. Okay? But you'll see it when we start writing code. Okay? So now let me talk about this and then this. So the different thing between distributed algorithms and non-distributed, the really new thing is this, the model. Because you're writing it on top of some model where nodes might fail. There's some kind of synchrony, it could be synchronous or asynchronous, partially synchronous. So when you write the algorithm, there is some model underneath. And that's part of the specification. But that's not, you're not controlling that. The programmer is not controlling that. You're given the model. And you have to write the algorithm for that model, okay? Whereas the safety properties and liveness properties, you are the master of these. You're the master of these two, but the model is given to you. It's like, write this code and it runs on open internet. Yes. So that's it. You have to write it for that particular model, okay? And if you change the model a little bit, things that were possible might become impossible, okay? So this is the specification part, and this is the implementation, okay? Here we have, I just showed it to you, event-based model. It's layered, it's concurrent, and this guy will normally be satisfying this properties. It will run on this model with these properties, with this interface. And then we'll have to prove it's correct, of course. Huh? And when there's concurrency, when there's failures, we have to prove that this code is right. Huh? Okay? So let me just give you some examples. Interface is the easiest thing. This actually comes from the book. Here's a very simple interface, a print module. There is one request and a confirmation. So confirmation is always going up. The request is going down. I print request, request ID and a string. Print, confirm, this ID has been confirmed as printed. Okay? Very simple. And here would be the implementation. Okay, so this is a very dumb example. Huh? I'm assuming that there is a primitive print operation, pseudocode. I can assume what I want. And so when I get a upon event print request, so that's a receiver, with the request ID and a string, I will print the string, and then I will trigger send a confirm. You see? This is a very simple implementation. Huh? Receives the print request, sends back the print confirm, right? It's a very simple example. Just to show you, there's nothing really magic or complicated here. Huh? Okay? Okay, now let me do a two-layer example where I have print will be the lower layer and there will be another layer on top. So I have a two-layer thing. This one is called bounded print. So here again is the interface. I do a bounded print request with ID and a string. I get a confirmation, which is, it has an extra return value, which can either be okay or not okay. So the bounded print is only able to print a certain number of things, some maximum number. If you go beyond that, it doesn't work anymore. So if I do a print request and it's already beyond that, it's going to send me a reply saying, not okay. And at the point you reach the threshold, when I reach like 1,000 or whatever it is, then I will get a magic indication coming up saying print alarm, saying, whoop, be careful, I've just run out of paper or something, okay? So this bounded print is implemented on top of print. And the way I do that is I say, I want to implement bounded print, and it uses print. The idea is that there's two layers here. I have bounded print using print. So here I now have my two-layer system. And this is the code for bounded print. There's an init event. This is automatically executed on startup. We're assuming that. There's an init event. And the bound is a local variable. It's set to some constant, the number of pages, for example. And then you have upon event bounded print request. If the bound is greater than 0, then I decrement the bound. So I'm just doing pseudocode. Bound gets bound -1. I do a print request. This is going down to the print module. And then if the bound is 0, then I do print alarm. This is going up. This is the alarm when I reach the threshold. And if the bound is not greater than 0, I will immediately send a print status not okay. And then there's a third piece of code. When I get the print confirmed, so this is coming from below, then I will trigger a print status. So I will send a message back up. So the print confirm comes from the print, and it causes the print status OK to be set. You see? So this is the code for bounded print, using local variable, doing computations. It's doing sends here, and I have 3 pieces of code that wait for messages. You see that? Init message, bounded print request, and print confirm. And messages are going up and down, huh? Okay, bounded print request goes down, print confirm goes up. See, so this is the kind of code we'll be writing. Okay? Of course, this is kind of a trivial, non-distributed example, huh? Later on, after the break, I show you more. And we'll see more and more interesting examples. But this, I just show it to you so you can kind of get familiar with the pseudocode. Huh? You see, it's not really very complicated, right? You understand it? Okay, so I'm assuming you're understanding it. Okay. Now let's go to something more interesting, which is the correctness, the properties. When we write the code, we're going to prove it's correct. So how do you write properties? And there's 2 kinds of properties that we have, called safety and liveness. So maybe you know that already. Have you seen already safety and liveness? Who has seen safety and liveness? Raise your hand if you've seen it. Everybody? A few people. Do you remember what it means? Okay, well, I'm going to talk about safety and liveness. And safety and liveness is formally 2 kinds of properties. I will give you intuition, but I will also give you a formal definition. And all properties are either safety or liveness. Okay, this is something you can prove mathematically. Safety, intuitively, bad things never happen. So when I run the algorithm, it never explodes. Okay, bad things never happen. And liveness is that good things will eventually happen. It actually does the work, okay, that I want it to do. So those are the 2 kinds of properties. Okay, so stupid example. If I'm looking at a student in this course, the safety property is that you should not fail the exam. And the liveness property is that you should take the exam. Okay. Or here's another example. Traffic lights. Okay, so the safety property, so I have green and red lights at each intersection. So this is an example with 4 cars, okay? More than one direction should never have a green light at the same time, okay? So you never have 2 directions here with both green. That's the safety properties. Because if you have that, otherwise it's bad. And the liveness property is that every direction should eventually get a green light, because it's actually very easy to satisfy one of those 2. The hard thing is satisfying both. Huh? So the easy way to satisfy safety is what? What's the easiest way? Just to satisfy safety? It's very simple.
All the way is red.
Always, everybody's always red. Okay, fine. This satisfies safety. What's the easiest way to satisfy liveness?
Always green.
Everybody's always green. But that either of those is not very nice, okay? So the real hard thing is actually satisfying both. That's why when things get hard and interesting, okay? Okay, so I want to give you formal definition. Throughout the course, we're going to be very precise on the properties, okay? Distributed algorithms are very subtle. They either work or don't work for very subtle reasons, and it depends on many things: the failures, the synchrony, That means we have to be very precise. And for all the algorithms I give, I'm going to give you formal properties of them in terms of safety and liveness, okay? And you'll see it already today. But let me give you a break, and then we'll start doing some stuff after the break. First, about safety and liveness. Whenever you want to implement something, so you have to know exactly what you're implementing. And the most important things then are the correctness and the system model. Correctness is safety or liveness. I want to give you a formal definition, but also intuition. And safety and liveness are properties. So first of all, what is a property of an algorithm? Well, it's a function, and it has one argument, and the argument is an execution. That's a big thing, huh? Remember, an execution is an infinite sequence of configurations with events doing the kind of things, okay? So it's a property of a whole execution. That's what a property is, a function of the whole execution that returns either true or false. So the property is either true for the whole execution or false. Notice it's not a function of a single configuration. So it's not like a function of a snapshot. It's a function of the whole execution, and that's very important. We'll see why. It used to be in the 1990s, when distributed system was still kind of an immature, messy field, like I said before, some people defined it using configurations. But we will see that that's actually not good enough. There's lots of things you cannot do if you define it only for configurations. It has to be on executions. Okay. And there's a mathematical theorem. I will not show you the proof, but if you're interested, if you're mathematically inclined, you can see the proof. This is from 1985. This is a very important and famous theorem. Any property of an algorithm can be expressed as the conjunction of a safety and a liveness. That means I can take any property of the algorithm and I can write it as a safety property and a liveness. So a pure safety and a pure liveness. Okay, so that's very interesting. The proof is actually very curious because it uses notions of topology and so on. But in order to see that, I want to define now formally what it is. Okay? Let me now define formally what is safety and liveness. In order to do that, I need two concepts. We're talking about executions, huh? So the prefix of an execution and an extension of a prefix. Let me make some pictures here. Okay, let me show that to you. So I am a very visual person. Some people are not. Some people love manipulating formulas. Your mileage may vary, but I love drawing pictures. So if I have an execution here, I start with the configuration, and this goes on forever. This is an execution, E. Okay, and here I have, let's say, C, K, and it keeps going. And these are the events. So this is an execution. Okay, a prefix is the first K configurations. So it's this. This is a prefix. So it's the beginning of an execution up to some point. Okay. With the events. So the C's up to CK minus 1, and the events up to EK minus 1. So there's other stuff in here. You cut off the tail. So it's the first part of the execution. And an extension of a prefix is just any execution that starts like this. So let me call this prefix P. Ends here. If I continue like this, okay, this new execution is called an extension of P. So this execution here, this is an extension of E. Okay? What we're going to do is we're going to look at the first part of an execution, we're going to cut it off, and then we're going to extend it in some different direction. It's like the algorithm does the same thing up to here, and then it starts doing different things. Fine, huh? Maybe messages arrive in different order or something. Many executions are possible, of course. Huh? Prefix and extension are the two concepts we're going to use. And now let me define safety, and then I'll define liveness. Okay? So safety, what does it mean? If I have an execution that is unsafe, so I'm violating safety, something goes wrong. Well, it actually, formally, the wrong thing happens at a certain time. Every execution starting, so there's some property P here. If the execution is not safe, every execution starting like E and behaving like E up to the bad event will be also unsafe no matter what it does after. So for example, I'm holding an egg, okay? And every time I take a step, I'm holding the egg, and it's a raw egg, and I drop the egg, splat, okay? Whatever I do after, I cannot fix the egg, okay? It's broken. So every execution, so here I drop the egg, okay? Whatever I do after, so I go here, or I continue here, or I continue here, any execution that continues after that will also be unsafe. When an execution goes bad, it stays bad. It cannot be repaired. That is the thing of a safety property. When it's broken, okay? So formally, so that's the intuition. Formally, it's like this. A property is a safety property given any execution E, and the property is false, so it's unsafe. Huh? Then there exists a prefix such that every extension of that prefix is also false. So that it actually goes bad inside the prefix. So in a safety property means that there is a place where it goes bad and it stays bad. Okay, that's what safety means. Okay? There exists a prefix, so no matter how you extend it, if E is bad, there exists a prefix, let's say here, this one, such that no matter what I do after that, even if I do different things, they will, all those extensions will be bad. So when it goes bad, it stays bad. Okay? That's the formal definition. Okay, so here's an example from a distributed system. Point-to-point message communication. And here's a property. A message that is sent from one node is delivered at most once. So 0 or 1 times, not more. That's a safety property. Okay? Why is it a safety property? Well, if the message is delivered twice, the property is broken. You cannot undeliver a message, okay? So you take an execution where a message is delivered more than once, and at the point when it's delivered twice, you cut it off, so you have a prefix, and any extension of that prefix, it will be delivered more than once. So they will all be broken. All the extensions will violate the property. So once you send the message more than once, it's all over, okay? So a safety property is a strong thing. Once it breaks, it's broken. Okay? You cannot fix it. If you can fix it, it's not safety, okay? Then there's no issue. If it's something that can be fixed, then we don't even talk about it, okay? It's part of normal execution. The safety is when you can't fix it, okay? See that? That's how we define safety. Okay, so that's safety. Now let me give you the other side of the coin, which is liveness. Liveness is the good thing, the good stuff. Okay? So liveness is kind of an opposite thing. So assume I have an execution E and P is liveness. So P of E is true. It's a live execution. It's good. Then for every prefix of E, I can always make it true. That means things, if there's one execution where it's good, always things are going good. Okay? And as long as there's life, there is hope. That's one way of seeing it. As long as you're alive, so the execution is going on, the good thing can happen. So that's also a very strong property. Yeah? As long as, if we have an execution which is alive, so it satisfies the property, that no matter how we chop it up, we can always satisfy that property. So an example that I like is driving a car. If I go from here to the beach, I drive to the beach, safety would be I have an accident and it's all over, okay? No matter what I do after the accident, I still had my accident. But liveness means I'm traveling, I have one trip where it actually works. Then I stop in the middle, I take a break. No matter what I do afterward, I can still reach the beach. Nothing is lost, okay? I can always still reach the beach. So if I have at least one good execution, that means no matter where I stop in the middle, I can still go on and reach the beach. So that's a liveness property, okay? And it's the definition. You can tell me, yeah, but maybe you'll have an accident later. Yeah, but that's not the point. The point is, this is a property of an execution. That means potentially, I always have the potential of doing the good thing. It's the formal property of the algorithm, okay? So that's the liveness, okay? So here's a distributed system example. This property P, a message sent is delivered at least once, which means once or more than once. That is a liveness property. You see that? That is liveness. Take the prefix of any execution where you deliver the message. If inside that prefix you've already delivered it, then you're fine. You don't have to do anything you want after because you're satisfied it. But if the prefix doesn't contain the delivery, well, you just have to make sure the extension does the delivery, and you can do that, okay? So that is a liveness property. It's a property, so it's clear, if I don't deliver the message 0 times, if I have it 0 times, all I have to do is deliver it later, and I'm done, and I'm live, okay? So the liveness property lets you do that. So liveness property lets you always do the good thing. And a safety property says, once it's broken, it's definitely broken, okay? So those are the definition of those two properties, huh? It's not an observed thing, it's the definition of those properties, huh? Okay, so I'm a visual person, so I will show you some pictures, but just one thing. So in the rest of the course, you're going to get lots of chances to really understand that, because whenever we define an algorithm and I give you the properties, I'm going to ask you. So that one, is it safety or liveness? What is it? Okay, so you get plenty of exercise. But here's my way of seeing it visually. Okay, your mileage may vary. This helps me a lot, but maybe it doesn't help you. In the top part, I have an execution E. Okay, assume safety is false. Then there exists a prefix, this is the prefix, such that all extensions are also false. Broken is broken. Liveness is here. Okay, so assume liveness is good here. So for every prefix, there exists an extension, at least one, that makes it true. So you can see the kind of dual properties, huh? Exist for all exist. So this is one way of visualizing the difference between the two. Okay? Okay, a little bit more intuition. A lot of words in language are kind of pointing towards safety and liveness. So, safety can only be satisfied in infinite time. That means in any finite time, you're never sure. When I'm driving a car, I can always have an accident, and you're not sure that it's safe until you actually arrive at the destination. So can only be satisfied in infinite time. During the execution, you're never safe, really safe. And it can only be it's violated in finite time. So when you crash, okay? And if you say you never, at most, cannot, that's kind of safety. Partial correctness is kind of safety word, okay? Liveness is opposite. It can be satisfied in finite time. I'm driving, after 2 hours, I reach the beach. I'm there. It's satisfied, finite time. But it can only be violated in infinite time. I'm driving, but I never actually reach the beach. I can only actually know that after infinite time, okay? During the finite time, there's always a chance I might get there. So it can only be violated in infinite time. Okay, so those are the two ways of looking at those two properties. So liveness words are eventually, it must be like this, at least. Termination is a liveness property. The algorithm successfully terminates. That's liveness property. Okay, so some questions for you. Okay, I said that we define safety as a predicate, a property, true for a whole execution. Why don't we just define it as a predicate, a property that's true for every configuration? So we define it like this, P of E. Why not define it like this? For every configuration in the execution, P of Ci is true. Okay? So this is the way we define it. It's a property of a whole execution. Why don't we just define it as, for all configurations in that execution, it's true? Why not do it like that? Well, there's a good reason. If we do it like this, I mean, something goes wrong sometimes. It's not actually good enough. Okay? So what goes wrong? If we say it's safe in every single configuration, how come that's not good enough? Whereas if we say it's true for an execution, we're good. How come? Can you imagine an example where an unsafe execution, you could not see it with this definition, but you would see it there? Actually, we saw an example like that just a little bit, a few minutes ago. No? Any? For every configuration in an execution, that configuration is safe. We could define it like that. See, this is kind of a subtle kind of thing, right? When I tell you something, you should never accept it uncritically. When I say do it like this, feel free to disagree, but justify your disagreement. So why is this bad? We actually saw an example just a few minutes ago. For all configurations, P of Ci is safe. Well, hint. The example where the message is delivered at most once. Well, a delivery is something that happens in a configuration, okay? Well, if I have two configurations, each one of them is delivering once, but together it's delivered twice, of course, But I can't see that if I only look at individual configurations, you see? I have to see the whole behavior. I have to see the whole thing. Because the thing that goes wrong, it might depend on several configurations. You see the example with delivery, for example? You see that? There's other examples too. But many safety properties, you can't see them if you look just at configurations. Okay? So that's one thing. Here's another thing. I told you, remember, that there's a theorem, okay, about safety and liveness. So, question. Is every property really safety or liveness or safety? So here's an example. Every message should be delivered exactly once. Safety or liveness?
Both.
Both? What do you mean? You have to say what you mean. Both?
Yeah, I mean it's both live and safe.
No, a single property cannot be both live and safe.
Oh, okay. I mean,
but you're on the right track actually. I am the way I formulated my question. I slightly misleading you. So is every message should be delivered exactly once. How does that fit in our thing where you have both safety and liveness? Well, here's the theorem. You go back here. Here's the theorem. Given this theorem, and I give you the property, every message is delivered exactly once. How does that fit with that theorem?
It's an intersection of both the safety and liveness.
See, yes, exactly. It's actually a conjunction, so intersection, conjunction. The safety property is it's delivered at most once, and this liveness is it's delivered at least once. And so if you take the conjunction of those two, it's delivered exactly once. So the safety is at most once, and the liveness is at least once. So it's fine with this theorem, you see? You have to split it into two properties. So single properties might be combining, but you can always split them, huh? Okay? Okay? So, you get it? Okay, good. Let's go on. I want to talk about failure now. Failures, and we'll start looking at some code. Failures. This is a very nasty thing that happens a lot in distributed systems. And in the model, there's two things. There's the synchrony, how long do messages take, and so on. And then there's the failures. What happens if things fail? And those two things, of course, they happen. You have to be careful. So we're looking at both of them. Okay? So let's talk about failures first. I want to be a little bit more precise than in the first lecture. So there's many different kinds of failures. The real world is a very complicated place. But there's actually 4 kinds of failures that are kind of reasonable ones that happen a lot and that cover most of what really happens. Okay? And it's called crash stop, omission, crash recovery, and Byzantine. Okay? There's 4 ways a node can fail. And that covers essentially, well, this is a good way of dividing this complicated space of possible failures. In any case, Byzantine is the garbage can that covers everything, but these 3 others are very nice places to cut this failure idea, okay? And a node that does not fail when we run an algorithm is called correct. Okay, when I say the node is correct, it doesn't mean it runs forever, huh? It just means that during the algorithm, it doesn't fail, okay? Might fail later. The first, simplest one is crash stop, and this is a very common one. The node just stops. Doesn't send, doesn't receive anymore. It just dies, okay? This actually happens a lot. If I take an axe and I chop my laptop, it will have a crash stop failure, okay? This happens a lot. Lightning strikes, crash stop failure. So this will be our default model, okay? Okay, now I'm asking you a question. What if this system crashes and I reboot it? Is that a crash stop or not? What is going on there?
It's a crash recovery.
There's two possibilities. It's either a crash recovery or it actually comes back as a new node. If my application crashes, like a database, whatever, crashes, and I reboot it, it's actually a new application running on the same hardware, okay? So usually what happens is that it's a new node when it recovers. There's also the crash recovery, which is what happens to databases, but we'll talk about that in a few minutes. So crash stop is like the default one, and we're going to do lots of algorithms for that. But there's more complicated ones. There's something called omission failures, slightly nasty one. So the node forgets to send a message. Everything is fine, it's just that one message it sends, and somehow it doesn't send it, or the message disappears. Basically, I'm putting an element in the out buff, and then some nasty little demon removes that element from the out buff. So the message, poof, disappears. Or the message is in the in buff, and some nasty little guy removes it from the in buff, so the node doesn't ever see it. Okay? These are send and receive omission, but actually, both of them is kind of omission. We'll say omission just means the message disappears. At least one message disappears. That's an omission failure. But everything else is fine. That happens, huh? I send a letter to somebody, it never arrives. But I'm alive, that person is alive, and if I send a second letter, it arrives. So that's an omission failure, huh? Okay? Okay. A third one is crash recovery. Okay? Crash recovery is a special one. Okay? Okay? So the node crashes, so it stops working. But then after some time, it comes back. It restarts in some initial state. And in addition to that, there is some stable storage, which doesn't go away. So the node's memory is two parts. There's a temporary memory, which disappears when the node crashes, and there's a stable memory, which does not disappear. So that one is like completely normal, it's never crashing, okay? So this is like a disk, a permanent storage device. So this is a funny kind of failure. So it's invented because disks, databases tend to fail in this way, okay? A database has a stable storage, and why does it have a stable storage? Because we want it to be reliable. So we made the storage that actually can survive crashes, which is much more reliable than the temporary memory, okay? So it can save the state. So this stable storage will survive crashes. If you save your state in the storage and crash, you recover, that saved data is back. It comes back, okay? That is typically how a database crashes in a bank or wherever. And the reason why it's special is because of the stable storage. So if your software is written in a certain way to take advantage of stable storage, then the crash stop becomes crash recovery. Okay? But you have to be a little bit subtle on this. Crash recovery is a little bit more subtle than crash stop. Because nodes can still go wrong, but in a different way than crash stop. So a node is faulty, that means it kind of goes wrong. If it crashes and never recovers, yeah, then it's really dead, okay? Or it crashes and recovers infinitely often. So what happens if the node is running, it crashes, recovers, a little bit later it crashes again and recovers again, and then it crashes again and recovers again, and it keeps doing that forever. So that kind of node is not good. Something wrong with it. Even though technically it's recovering, it's unstable, okay? So that is also considered to be bad, faulty. A crash recovery node, it only recovers a finite number of times. Okay? It crashes and recovers, and that's it. Let's say once, for example, or twice, and that's it. It will eventually, after a finite time, do no more crashes. So if I'm writing an algorithm for a database, I have to assume this. Because if the node is unstable, algorithm might not work. Okay? So you have to assume this. So it has to be kind of the crash has to be kind of a transient or temporary thing. For example, a piece of dust got in the disk or something, it crashes, but then it reboots and everything's fine. Okay? That's okay. But if there is really something wrong with the disk, and it keeps crashing forever, over and over, then the node is considered faulty. Okay? So that's crash recovery. So you see, this is a little bit more complicated kind of failure mode. Huh? And the reason why do we define this one? This has a formal definition. Huh? So the reason why we define this is because we have a physical device that's obeying this, okay? Which is the disk in a database. And then the final one is the Byzantine. So this one is really the worst case. The node can behave arbitrarily. It can execute anything. It can send any messages. It can be malicious. It can be very smart. There can be some super genius there trying to figure out the rest of the system. Malicious node might collude. That means several malicious nodes might talk to each other and together try to do something bad. Work together to break the system, so that's called collusion. All of that is possible in a Byzantine. So that's really the worst case. So you might say, why not just make all algorithms Byzantine, and then everything's fine, and you don't have to worry about failure, right? That could be done. Why isn't everything always doing Byzantine fault tolerance? Because that case, we don't have to do anything else. We don't have to do recovery. We don't have to do anything else. So that could be done. Why don't we do it? I mean, why don't people do like that? It could.
It's hard.
Well, the code is more complex, but these algorithms are known, and there's libraries. But there's another reason, kind of a very practical reason. These algorithms are very slow, okay? It's like the analogy is like traveling with a passport. If I enter a country, I check the passport at the border, they check it, I'm legal, I go in. But once I'm in, I'm free to do whatever I want with no overhead. I can go to the bank, I can go to the stores, I can spend money. But in the Byzantine, it would be like every time I try to do something, I'm completely checked again, over and over and over and over, always. So every single thing that I do is checked thoroughly using cryptographic protocols. So that would make my life miserable, okay? So that's why that's not done in the real world, but it's also not done in computing systems. It's only done when the Byzantine, the maliciousness is fundamentally part of the system. Like in a cryptocurrency, for example, there is money involved, real money. It's not just people playing games, it's real hard cash. So breaking the system gets you real money. That means there is a strong incentive to break the system. So they have to use Byzantine algorithms that are very well implemented, okay? But that's a special case. Okay, if you look at these 4 failure types, they're actually hierarchy. Each one is kind of a subset of the next one, okay? So for example, crash stop is a special case of omission. That means if I make an algorithm that can handle omission, it will also handle crash stop. All crash stop failures are also omission. Okay? It's an omission where after a certain event, I forget everything. That's allowed in omission. So that exactly is like a crash stop. Okay? So crash stop is a special case of omission. What about crash recovery? Okay? Okay, so crash recovery, omission is actually a special case of crash recovery. And the way to see that is to see how you can implement omission using crash recovery. Okay? Assume you have a special case of crash recovery when you only have stable storage, only the permanent and not temporary. Okay, in that case, crash recovery is identical, because when you crash and recover, it means you're just forgetting the message, okay? And so no state is forgotten. So while you're crashed, you're just emitting messages. And the recovery could be very fast. You could maybe just emitting one message. So then you're exactly the same as omission. But crash recovery is actually more than that. It has more kinds of failure than just omission, because it might have volatile, so kind of temporary memory. And when it crashes, this memory goes away. And this is kind of, you could say it's like amnesia. I forget something. Well, omission doesn't forget anything. So crash recovery is like omission plus forgetting something, amnesia. So crash recovery can do all the failures that omission does, plus a little bit more. So omission is a special case of crash recovery. And final, of course, crash recovery is a special case of Byzantine, because Byzantine allows anything, okay? So you have this hierarchy. So here you have all the possible failures of crash stop. Omission can do these plus more. There's even more possible failure modes. Crash recovery has even more, and Byzantine has the most. So you have these four hierarchical, okay? Usually we're going to stay here. That's already very subtle. And sometimes here for this. And actually, probably we won't have so much time for looking at Byzantine. Byzantine algorithms are quite complex, but there are many, many of this. This is a very active research area. And now, of course, it's very much in the media because of cryptocurrencies. So these are certain kinds of Byzantine algorithms, okay? But most of the time we'll be sitting here in the crash part, okay? Okay, now let me start writing some code. So I talked about node failures. Now I want to talk about network or channel failures. And then we write some code, okay? So how do networks fail? Well, the simplest kind of failure is when the message goes through the network, it arrives with some probability, 80% of the time. And it may fluctuate in time also. Sometimes you may have a lot of loss, sometimes you have less loss. There's certain chance that the message just disappears, okay? This is the basic thing. This is the foundation. In fact, the whole course is built on fair loss links. This is the only assumption we will make on the network. This is the connection between my course and Olivier Bonaventure's course. That is the only connection, okay? It is fair loss links. Let me make a picture of that. So we have fair loss links here. The whole course is built on this foundation. It's interesting to know, huh? That's the only thing I'm going to really assume from the network. That a message will be sent and will arrive with some probability, and that there's some chance it disappears. And what I want to show you now, today, is I want to show you some code. I want to show you how to implement perfect links, which never lose messages, by using only fair loss links. So this is the only one we really assume, okay? But today I want to show you the code for perfect links, which is delivers any message sent exactly once, okay? And I will show you a system with 3 layers. So the fair loss is like the underlying layer. This is the assumption. And the one that I really want to show you is the perfect link. And for some interesting reason, it's nice to have an intermediate layer called stubborn links. So I'm going to show you code with an abstraction with 3 levels here. Okay? A stubborn link is whenever I send a message, it's delivered infinitely many times. Kind of weird, but at least the code is very simple when I do that. Okay? So let's start. Fair loss link. This is what it looks like. I have 2 nodes, I and J. This is the interface. I have fair loss point-to-point send and a fair loss point-to-point deliver. So I do a request here, and there's an indication coming here. And I can also do it in the other direction. Okay? This box, this rectangle, is assumed. It's something that the system gives me. Okay? This is the interface. There's a request, fair loss point-to-point send. This is the name of a destination node. This is a message M. And when the message arrives, there's an indication, so going up on the other side, which tells me where the message comes from, the name of the source node, and this is the message. So M is a random data structure, any very complicated data structure, okay? And this thing has 3 properties, okay? These are the 3 formal properties of fair loss. So I'm assuming this. FL1, FL2, and FL3. The first property says, if a message is sent infinitely often from PI to PJ, and neither node is crashing, then it will be delivered infinitely often. This is kind of the loss. Maybe some messages are lost, but if I keep sending, it will eventually keep arriving, okay? Maybe only 10% of the messages arrived, but it's not 0, okay? And the second one, if a message is sent a finite number of times from I to J, then it is delivered a finite number of times. The network will not infinitely duplicate the message. And the final one is no creation. No message is delivered unless it was sent. That means the network is not going to just send me a message, some random thing, if nobody sent me. Okay? So these are the 3 properties that I need. And each of them is a necessary property. Okay? That's given. I'm not going to show you the code for that. So for example, IP gives me this. Okay? The Internet Protocol, or UDP, for example, is something that gives me this. Okay, I'm assuming that. Is that true? Think about it. So these are the 3 properties given by some Internet protocol, and I'm assuming they exist. And everything else is built on top. So the next step is the stubborn one. So I'm going to build this one and then this one. So now we're going to start writing some real code. Okay, so this one is now stubborn point-to-point. So again, there's a send to a destination and a deliver, a request and an indication. And this thing has 2 properties, SL1 and SL2. If a node sends a message M to a correct node PJ, and PI does not crash, they're both correct, then PJ delivers M an infinite number of times. So it keeps repeating over and over and over and over again. And the second one is no creation. So there's no finiteness here. It keeps going over and over and over again. It's stubborn. So why is that important, actually? Why do I need that? Well, it's because of the loss okay? To guarantee to deliver M, there has to be something like this. If it was only finite, then there's always a chance that M will never get delivered. That's why it has to be infinite, okay? So those are the two properties, and here's the code, okay? So, here, so I'm going to use the fair loss. I'm going to have a local variable, sent. The sender will store that message in the local variable, and that's a set of messages, and I will have like a loop sending the messages that are there, okay? So here's the code. It's actually 2 pages. So I have a local variable, sent. I am using fair loss links to implement stubborn links. I have a timer. I can do start timer time delay, and after that delay I will get an event timeout. Okay? So when the timeout event happens, I have a for loop. For all destination M element of send, I do a send, a trigger. So basically I resend all the messages in the send set. And I start the timer again, so that it does it over and over again. And then the second page, whenever I do a send, I actually just add the message to the send set. And whenever I do a deliver, I just pass it up. So the way the stubborn one works, so the stubborn one is like this, huh? So when I call the stubborn one, it adds the message into the send set. So there's a send set here. And there's a loop here for all that will send it, all the messages in the send set over and over again after a certain time. And whenever a message comes back, it's just passed up. Whenever there's an indication coming back, it's just passed upwards. Okay? So sending down is just adding to the send set, and going up is just delivering. Okay, you see how that works? So this is the whole code. This very four little chunks of code upon event, chunks of code. So this is how we're going to be writing the algorithms. Okay? So you see how the stubborn links are working? Now you can actually prove formally that the stubborn property is satisfied. So now we have to actually prove that these two properties are satisfied by that code given this code. That's a formal proof, okay? So I'm not going to do it right away. I want to show you the code for the final one, which is the perfect links. So that's this one. And it's going to use the stubborn links. This one is called perfect point-to-point, okay? It is going to have a send and a deliver, and it has 3 properties. See how we're doing it? We're always defining properties, okay? Reliable delivery. If neither PI or PJ crashes, every message sent to PJ is eventually delivered. That's good. Every message is delivered at most once. Okay? Okay, so it's delivered, that means at least once, huh? Here, at most once. Together, that makes exactly once. And then there's a final one, no message delivered unless it's sent. So the network is not going to create weird messages. Okay? Okay, now I want to ask a question. I have these 3 properties. I want to know whether they're safety or liveness. The first one, is that safety or liveness? Every message sent by PI PJ is eventually delivered by PJ. Safety or liveness? Liveness. There's a liveness word in there. Huh? So the good thing will happen. So that's liveness. What about the second one? Every message delivered at most once.
That's safety.
That's safety. Because if you deliver it more than once, you're dead. So that's safety. What about this one? No message is delivered unless it was sent. So the network is not going to create some random piece of garbage as a message and deliver it.
That's also safety.
That's also safety, because if it does that, the system is broken, huh? That's also safety. Okay, you see that? So we see that this is a liveness. So we have both safety and liveness, so we're good. And how does it work? So we're going to use the stubborn links. And again, we have a local data structure, which is going to be a log. It's basically all the message that were delivered. We're going to keep them in a log. And if the message comes again, we're going to check if it's already delivered. We're not going to deliver it a second time. Okay? So this is the code. So it's actually just one page of code. This one has a log, which is a delivered set. Okay, the send is just going downward. So if I do a send here, it's just going to forward the message down to the stubborn link. And the return is going to check whether the message has already been delivered. If it hasn't already been delivered, then I add it to the delivered set and I deliver it. Oh, but if it would arrive a second time, then I won't deliver it. Okay? So that means if the message comes many times up here, well, it's only the first time that it's going to be delivered. So together, these two will in perfect links. Okay? And you can prove it. So why did I write it this way? In fact, this is very inefficient. This stubborn link is going to be delivered infinite number of times. How stupid can you get, right? And this log here is just going to keep growing forever, right? So why am I implementing it this way? What do you think? Why am I implementing this way? That I will end there because we're almost done. Why am I doing it all so stupidly? Well, actually, because of Donald Knuth. Premature optimization is very bad. This is a very inefficient algorithm, but it has the incredibly nice property of being correct. Okay? That's very, very nice. And when we start looking at distributed systems, where you have concurrency, distribution, partial failure, just getting correctness is a major achievement. Okay? We can always optimize this later. TCP will optimize by keeping sequence numbers. But there's no reason to do that here. Here, we just want perfect links. Optimization is always done later, okay? So there's a very good reason why this is not the most efficient algorithm. It's because this algorithm is by far the easiest to prove that it's correct, okay? Correctness is very important. Efficiency is nothing if your algorithm is buggy. Okay, so let me stop there. I think we're done for today. And so next week we go on, and I'll talk about synchrony and failure, and you will get even smarter than you are this week.